All right. Hello and welcome to our PAT forum. My name is Oliver Mandal and I'm product manager at Hellma. Today, I would like to welcome you to our webinar with PAT specialist Dr. Chad M. Shade on the topic Transforming the Chemical Manufacturing Industry through Process Analytical Technology, Retrospective. I would like to point out that we will record the webinar slides. The distribution of the video is intended without displaying participants or comments. Your participation or personal details will not be visible in the recording at any time. You will receive the link of the video by email. Today's expert is Dr. Chad M. Shade. He studied at the University of Pittsburgh and received his PhD in analytical chemistry. He began his industrial career as an analytical spectroscopist at PPG and later worked as a process technology chemist. He gained extensive experience from developing modeling concepts up to managing the global project portfolio. As an experienced process chemist, he is currently head of the global PAT team at Albemarle Corporation. He manages the global efforts in PAT research and implementation with a focus on multivariate sensors and chemometric methods. So now I would like to hand over to Chad.
So thank you, Oliver, for that really kind introduction, and thank you, Hellma, for hosting this wonderful event, and thank you to the audience joining us today. So PAT is a very small, tight-knit community. And in the spirit of that community, I was hoping to give back to PAT by sharing a few examples that I've collected over the years at companies where PAT was at its earlier stages. So sharing what worked well and perhaps what didn't work so well. And I think that this presentation is going to speak to those who are about to set foot on this journey themselves, or perhaps those who help PAT along the way, our vendors, as well as some whimsy thrown in for the seasoned veterans. So you all know why you're here today. It's because your processes are extremely manually there's a lot of manual intervention. Operators are having to be exposed to hazardous conditions, while the fate of the batch it relies on a 1 gallon sample, which may not be kinetically inert, thermodynamically stable, or statistically relevant. Inline sensors, on the other hand, allow us to collect data at a much higher frequency, much higher than even our speediest operators. And algorithms convert that incoming data into actionable information virtually instantaneously. And one of the advantages of that is the higher level of granularity one now has of their process to start to conceivably optimize that process for uptime or quality. So in my agenda today, I wanted to talk about 3 areas that I think are perhaps underestimated for PAT projects that I've seen time and again. So articulating value of the project at the ideation stage, designing interfaces during the specification stage, and managing the expectations, which is very key during project execution and beyond. And if there's time remaining, I would like to share an example which may not be so crazy, but I firmly believe that we can build stronger communication through our organizations by introducing principal components analysis, a wonderful visual technique. So jumping right into articulating value, I think it's really important that you identify in your organization the person who owns and maintains the roadmaps. These are documents, very sensitive documents that may not be distributed, but they track or chart the product and process life cycles from launch all the way through to obsolescence. And that's key because you don't want to base your business justification on a product that's phased out in year 2 of your project. And keeping with that, let's talk about those targets for a moment. So you generally want to prioritize, especially for batch processes that make dozens of different products, the high volume products, perhaps as few products as is necessary to add up to 80% of the total volume. Now, you may find a product, for example, that you could cut half the cycle time on, but if it's only made twice a year, that's not really going to help you get to your return on investment, your ROI term. So keep that in mind, and you can chase that 20% tail just as soon as your ROI is done. And then I think it's very, very, very vital, extremely important to sharply delineate savings in terms of soft and hard savings. So soft savings, it's very important to identify these opportunities and to change your process based on those opportunities. But they may not necessarily translate to value, to additional batches, to additional sustainability savings, etc. Those are the hard savings, converting the opportunity identified and changing it to hard savings. And that transition can happen with very serious conversations with your plant managers, creative scheduling, and campaigning batches, for example. So here are the levers of PAT value creation as I see them. Safety, of course, is number one. Quality, fairly obvious. Time savings, which I'm going to spend the next few slides discussing. Sustainability, which has become quite an area of discussion, especially in the countries that do have a carbon tax. And cost avoidances. These are things like the effect of substandard product loss and having to rework or dispose of those lost products, deferring new capital investments, and so on. And as far as the kinds of projects that the PAT team works on, I break it down into categories of your known knowns and your known unknowns. So for your known knowns, these are things that you can already understand from a plant manager's record of runaway reactions, for example. So they'll know which are their problematic processes. I will caution you, though, that you probably don't want to justify a project solely on the number of runaway reactions, just in case one happens on your watch, which would be absolutely devastating. And then there are the value streams that must be actively developed. I will actually be focusing most of the discussion on just these first two, cycle time optimization and sampling frequency optimization, but I'd be more than happy to come back another time to talk about the others. So let's take a step through the decision tree process for cycle time and sampling frequency optimization. And notice I say optimization and not always reduction, and that's important. Because one could imagine, for example, in the case of cycle time optimization, needing to increase cycle time in order to improve quality and or sustainability. And for sample frequency optimization, it's not necessarily something which adds value to the process, but certainly to the project and improving the model in taking more samples. Now, transitioning over to cycle time reduction now. There's a very important question that comes up first, and that split decision is very, very essential, and that is there any demand for your product? If there isn't, it's not the end of the world, but let's cover first when there is a demand. So if you're able to gain back so much capacity, maybe not necessarily across this reactor system, but several located around the globe, then it could be conceivable that you could avoid constructing a new $30 million reactor or building a new facility. In that case, there's a major capital cost avoidance there, in addition to the added sales. Now, don't worry if there isn't, of course. The next question is there enough capacity to produce additional batches? And if there's yes, then those additional sales are definitely something which adds value to the project. But if there's not, then we start to ask questions about sustainability. So can you conserve utilities during that downtime? Can you turn off the pump, the motor? Can you turn off the heat source, etc.? If you can, or if you can start the next batch a little bit sooner or do some creative scheduling, you can get at sustainability numbers. And if you really can't do any of that at all, it's time to have a very serious conversation about your project and a conversation with the plant manager. Now, going back up to the top, if there isn't any demand for your products, then at the very least, it's important to ask, do you do tolling today? If you do tolling, is there an interest to insource that outsourced cycle time? If there is, then once again, that's a cost avoidance because tolling premiums are quite high. But if there isn't, then you can start to ask questions about what to do with that extra time. So if there's enough time to reduce the work days or shifts of that process, then of course, going from 24/7 to 24/5 or going from 3 shifts down to 2 or possibly even 1 has serious utilities that could be conserved for sustainability. And notice that I don't say of the facility. I'm not saying that we need to shut the facility down for those days or hours. It's just that process now. The process that you're working on in your project is now more capable and potentially doesn't need babysitting. And then quickly, just to talk a little bit about sampling frequency optimization, once you reduce sampling frequency, you immediately improve safety and sustainability. And as long as you're not just running and recording the testing, meaning your batch isn't waiting on those results to move it forward, then you can eliminate those endpoint samples at the very least, and that has implications for back in the cycle time optimization. But my real big take-home message for all of this is think holistically, because some of these buckets of value compete with one another, and business needs shift all the time. This brings me on to my second topic, designing interfaces. Robustness, representativeness, and cleanliness. These are all major implications of moving the analyzer out of the lab and into the process. So mechanical and chemical failures are very common. Think not just about your max temperatures allowed for that equipment, but the effect of thermal shock, going from very hot to very cold, or the opposite. If there's any question about chemical compatibility, coupon studies are great. And if your vendor is open to that, I highly recommend pursuing those. For representativeness, we kind of know that recirculation lines are perhaps the best place to locate a flow cell or a probe. And I would also recommend that if you don't know what theory of sampling is already, drop everything, pick up these papers and read about it. It's a dense read, it's a challenging read, but it is very rewarding for the dedicated reader. And you'll see what I mean by that when you get to things like the variogram experiment. And then cleanliness is essentially important. I mean, if you look at an analytical lab, we clean all the time. So in the process, you need to make sure that analytical surface is refreshed continually. And the good news is, if you're already considering representativeness and high turnover rates of your material in front of that interface, then you're probably very close to being there in terms of reducing fouling. So when in doubt, seek your process flow simulators. Of course, the start of any good design for an interface is considering what is your right tool for the job. And I use this modified and oversimplified Jablonski diagram just to illustrate the differences for the most common spectroscopic techniques we have in PAT. And just by doing so, you can see which are actually complementary. So Raman spectroscopy, whether you're talking about Stokes or anti-Stokes, the difference in those energies is roughly concomitant with the energy we probe using IR spectroscopy. The only difference is the resonance condition that satisfies these phenomena are net dipole change across a vibrational mode versus net polarizability change across a vibrational mode. You can also see, or if you understand spectroscopy and selection rules and allowedness of transitions, why the NIR transitions are so weak compared to IR, 100, 1,000 times weaker. It's because of, in many cases, consequences of quantum mechanics. And you can also see from this picture why Raman and fluorescence are sometimes at odds with one another, because we want to try to increase that energy of the laser as much as possible, but at the obvious risk of promoting and accessing that excited state envelope. Now I'm trying to tie this to the business in terms of sensitivity, selectivity, and reliability of these techniques with a huge, huge disclaimer. My experience may be very different from your experience. I have the experience, for example, with a 785 nanometer laser for Raman. Your experience might be 532 or 1064, and thus your sensitivity might be different. But it is still a useful exercise, because if somebody were to say to me, Chad, I want to use NIR because I have an analyte at the 1 ppm level, is that possible? And I would probably say, no way. NIR is more suited for the 1 weight percent or possibly 0.1 weight percent level of sensitivity. If you really want to get down to ppm or below ppm level, then fluorescence is definitely your technique. It's far, far more sensitive than most. Of course, it takes a huge hit with selectivity. These spectroscopic features are very broad and overlapping. And unless you do something like time-resolved fluorescence spectroscopy, you're not going to be able to be very selective with that technique compared to some of the others like Raman with its very sharp transitions. And then reliability is kind of a catch-all term that I use to kind of even the playing field among some of these techniques. I will say that NIR is one of the more common techniques across all of PAT because of its robustness. But even still, if you don't take measures to control temperature absolutely, or at least measure it very precisely, then you're going to accidentally calibrate the world's most expensive thermometer. And similarly with Raman and fluorescence, if fluorescence is a big hamper to your Raman signal, then you're basically, instead of a Raman, you have a very expensive fluorimeter. I could really have gone all day on that Jablonski diagram, by the way, but moving on to our last but certainly not least topic here, managing expectations. It is so important. And the reason why it's important is because business is date-driven, science data-driven. You have to be very bilingual and sensitive to that fact when you're putting together a technical presentation or you're putting together a presentation for the boardroom. And that carries over into discussions like, when does the return on investment begin? From a business standpoint, in some ways, this is unrevocable. It's capital centric. It's when that physical installation is complete, that's when the time clock starts for your ROI. And the science is we would much rather it be more model centric, because lab studies and pilot studies can only go so far, but they can bridge the divide. So I encourage everybody to try to see how to shorten that delta. But if you're going to try to make it a model-centric discussion, then you need to define the metrics for model development more precisely, because business, for whatever reason, has latched onto the R-squared value and the predictions themselves. Whereas as a chemometrician or a data scientist, convergence criteria is really how we need to start shifting that conversation away from R-squared value. And distances are very important, which I'll cover in the next few slides. So one of the most common questions I get is, how many samples do you need, Chad, right? We can't do this in perpetuity. And of course, that is not our expectation. But this illustration, I think, does a fairly good job of representing the work, which all begins, depending on where you want to claim it begins, with data acquisition. And we need that data in order to build the data sets. And I want to say that 90% of the work of a chemometrician is spent contextualizing and curating these data sets. Once the data set is prepared and you've superimposed all those layers of subject matter expertise, then exploratory analysis and model calibration should fall fairly quickly. But you may get to model calibration and discover there are gaps in my calibration, or there are clusters of samples here, and I need to understand what's going on. And that takes you all the way back to data acquisition. But ultimately, the ultimate goal is to drive this towards automated evaluation, not manual interpretation. So how do you answer the question, right? So there's a number-based question. You could say, oh, well, I need 30 samples to do this. And maybe that's a good start. But if any good CTO is going to listen to you very carefully and say, okay, Chad, I'll give you twice the head count to get that 30 samples in half the time. And that's not going to help you, because really what those 30 samples need to do is describe a certain amount of variation, which you could try to be a little bit more clever and say, oh, I need 10 times K+1 samples so I can kick 60% to calibration, 40% to test set validation. And basically you're going to wind up in the same set of circumstances where it's numbers based, more or less. I would argue that convergence is perhaps the best way and the only way to go here, which means you need to teach your organization to understand what it means when you need the root mean square error of calibration to approximate the root mean square error of prediction if you have test set validation. If you don't have a regression model, then of course cross-validation would suffice. And then also, and this is slightly different, the nuance is there, root mean square error of calibration approximating the root mean square error of the measurement. I'm talking about the primary analytical method, because your model, if it's a regression model, can by definition only be as good as the test you're training it to replace. So that's very important. And now your model starts to drift, or you need to do a maintenance cycle. You're not going to say, oh, well, I just need another 30 samples. I just need another 30 samples and so on. You're going to say, oh, my model has converged within a certain number of factors of the root mean square error of calibration, and so on. Trust me, it is worth the effort to save you a headache further down the line. And I see that we have 5 more minutes in the presentation. So I'm going to move through an example with you all, which is a further example of how I think we can use these algorithms more, not just as the means for guiding a process, but also guiding the organization, teaching them what this is all about. So before you is a data set comprised of 80 radio wave oscillations from a pulsar. It is a tangled mess of rainbow-colored spaghetti. Nobody knows how to interpret this except for a highly trained spectroscopist. And even if you had one on staff to do that level of interpretation, to tell me what are the patterns and what are the outliers, they're not going to be able to do this kind of analysis every 100 milliseconds. Instead, you need some kind of algorithm like principal components analysis, which turns down the volume on everything else in this tangled mess and turns up the volume on the variation, which you can see right here in the loadings plot. It's so easy now to answer the question of patterns because 66% of the variation depicted on the left-hand side is now contained within these hidden data structures in your loadings plot. And the relationships between these samples, the magnitude of the variation contained within each, is explained across each of these axes in a scores plot. So these are principal components, and you can see if there are any interesting patterns here as well in terms of sample to sample relationship. And this is the great thing about PCA in terms of assisting the spectroscopist. And I promise this is the only equation that I'm going to use in my entire presentation. But essentially, it works by factoring out the average spectrum. So you literally calculate the average and factor it out. And then you search, the algorithm searches for the largest source of variation contained within your spectra, decomposes it into scores and loadings plots, and then moves on to the next orthogonal source, and then the next orthogonal source, until you have a certain amount of variation explained in your PCA. So up top, I only have 2 PCs because I think 2 PCs is what the human brain is comfortable looking at in one go. But in this model, I worked it all the way up to 5 PCs, which is where I thought I saw noise enter into the equation. So we'll come back to that. But now moving on to the outlier question. For that, I want to start rearranging this data a little bit. So I got my spectra in the top left. It doesn't need to have color. And I like to position the loadings plots directly below the raw data because it's in the same scale or units. And there you can see where these patterns overlap with your processes and so on. But to really answer the question of which of these samples are outliers or suspected outliers, I should say, it doesn't really do a lot of good just looking at scores plots. You need to start introducing model health statistics, model health diagnostics, which I believe are absolutely essential to your organization. So things like the Hotelling's t-squared, which is basically the total distance from model center. It subsumes all of the scores values, in this case, 5 PCs. And you can introduce the thresholds the same way and see that there are a number of samples which poke up above the 95 or 99% threshold. But that's the captured variation, right? Your scores values capture variation described by loadings plots. Then there is residual information that's not captured by your model. That's contained within your D mod X or your Q residual, your F residual, whatever your organization uses to describe them. And this distance from model center could mean that there's a contamination in your spectrum. And when I look at Hotelling's and D mod X together, what I'm really looking for are those samples which have high both. And you can see right here that samples 51 and 45 have the highest D mod X and Hotelling's values. Now you can go back up to the scores values and see where they diverge along each PC. And as luck would have it, it's in the first 2 PCs where 45 scores the highest in PC1. PC1 is this curve in the loadings plot. And when you look at sample 45, it makes real good sense why it has a high D mod X value. And same thing for 51, although 51 is aligned along PC2. So PC2 has high signal in this location. Sample 51 has high signal in that location as well. But if you look really closely, which you probably can't do in a presentation that is live, samples 45 and 51 are ever so shifted to the right compared to PCs 1 and PC2. That means there's residual variation in samples 45, 51, and that is why they have high D mod X values. So you see, if you just went by scores values, you would not necessarily understand everything that we just discussed. And I think that this is such a wonderful visual technique that I'm going to take it one step further than spectroscopists typically do. And I'm going to demystify PCA by reconstructing the original data set using only PCs and the average spectrum. So I'm going to fan out the original data set in a stacked plot so that you can kind of see samples 45 and 51 a little bit more clearly among the rest. And now I'm going to add in principal components to the average spectrum and see how well that approximates the original data set. When I add the first two, so that's what we saw in the previous slide, that's 66% of the variation. And if you squint your eyes, it looks like the original data set, but there are obvious omissions in terms of the variation. And specifically for samples 45 and 51, I've put the labels in precisely the same location in the original data set. The center and height of these peaks is very different. When I add 3 more PCs, so 5 PCs total, you can see that now the labels 45 and 51 are very close to the center of these peaks. However, the width of these peaks is not very well described by 5 PCs. And when I did a little bit more investigation, I looked at PCs 6, 7, and 8, and I realized that perhaps there was not as much noise in those PCs as I had assumed initially. So when I add those 3 PCs, now 8 total PCs, you can see that the centers and the shapes of these features are now very, very close approximations of the original data set. And if you look very closely, so a keen eye will look elsewhere than samples 45, 51 and see other areas that could be improved. But I digress. This is such a wonderful technique. Data science uses it predominantly to reduce noise. And you can see that the noise that's in the baselines has also been reduced as a function of PCA. But where a spectroscopist or a chemometrician takes it one step further is interpreting the chemical and process data. So just to recap, I see we're at time here. If you only had to take away 3 messages from my presentation, it's articulating value, be holistic in your pursuit of different targets, and be very, very careful to identify what is an opportunity that's been identified versus one that has been realized, hard and soft. It's designing interfaces. Your interface needs to be robust, analytically clean, and also statistically representative. And lastly, managing expectations. Business is data-driven, science data-driven. It can lead to so many clashes if you don't give it its proper respect. And hopefully that example that I shared helped you to be inspired for how you can introduce some of these statistical concepts in your organization. And the next time you improve your model, you don't leave the conversation to just R-squared values alone. You start talking about distances and convergence. And with that, I would like to once again thank all the members of the Hellma team for organizing this forum and to the audience members for being active members of our community. I would be very happy to take any of your questions.
All right. So big thanks, Chad, for the awesome talk. I really enjoyed it, and I'm sure our audience found immense value in your words as well. You have the option now to ask questions. Please click on Q&A at the top menu of your screen and send in some questions if you did not send already. Here's the first one. Chad, what are typical or what are the biggest hurdles for the realization of a PAT project from your experience?
Yeah, I mean, I could talk about technical challenges. I could talk about organizational ones. One of the biggest challenges is, when you're forced to take on something which resembles a push project. So there's pull projects and push projects. A pull project is one where the facility is pulling you in. They really want this technology. Whereas a push project is one where it kind of feels like you're the one trying to drive it and get them excited and motivated. And my advice would be to try your very best, even if it is a push project, make it seem like a pull project. Communicate that value, get buy-in from everybody who's involved, collaborate very, very closely. And the other thing I would say from a technical standpoint is your primary analytical method development. It'll get you 9 times out of 10. If you're doing a regression model, like I said, by definition, you can't get more, when you're correlating, you can't get more precise than the primary method. So do the homework, ask the questions, make sure that those primary methods are not giving you random numbers.
All right, thank you. See, is there a rule of thumb how much of the process time could be shortened? I would guess that will depend very much on your process, doesn't it?
Yeah, I mean, a lot of my presentation today was geared more towards batch processing, more so than continuous. But in a batch process, we typically have a lot of kinetic holds in place. So there's a 1-hour hold after all of the raw materials have been charged in. There's a 4-hour hold. generally those are the places to look first, because a 1 hour hold, why is it a 1 hour? Well, because that's how long a lunch break is, right? Is it 15 minutes? Is it an hour and 15 minutes? Do we need more time? So I would suggest, anything that's given over to kinetics is a good place to start. If there's too much happening with a thermodynamic change, then that can get quite challenging as your concentrations, your temperatures, and all those other factors are changing simultaneously.
Okay, then one person asked, do you recommend any software tools for managing the contextualization of the data?
Well, that's a really good question. Yeah, so I've used JMP in the past, but really, what you need to do is pull in right next to your spectra all of the test results that you want to correlate to. So they need to be matched in time. And any other process tag that's out there that could help you contextualize the data. So I'm talking temperatures, pressures. If you have your tanks on load cells, those are excellent as well. And any other process information is just a new column that you match once again the time to your spectra. And that really is what the job is all about. That the algorithms themselves, they function in milliseconds of time. They're very, very quick. And, doing exploratory analysis is a couple of hours of work, sitting down. But the data set preparation, if you don't have Python scripts, or if you don't have, some way to bring in all the tags in through the SCADA so that they're matched in time, it can become quite a headache. So yeah, Python is great if you have anybody in your team that has programming skills. I know that some organizations would prefer there to be a complete commercial business solution. And certainly I'm sure that there are those out there. I would have to think about that a bit more.
Mm-hmm. Okay. Another question, what's your opinion on PAT robustness during a manufacturing setting and relying on the results for real-time monitoring?
Yeah, so nothing is without risk, right? So I think you can definitely take some steps to reduce that risk, and there's going to be a phased introduction here. Would be my recommendation, where you have more or less the inline and still the offline sampling happening more or less simultaneously. But then perhaps you can move to doing skip lot testing on the primary technique. So maybe you do a skip lot of 1. So every other every other sampling point is actually sampled and tested. Then you move to 2 to 5. And over time, what you're doing is building confidence in the team. You're developing those HMIs that the operator can see. They can understand that this number, which is changing, is tied to the process and hence, value. And hopefully, ultimately, what you get is pushing that primary technique to more auditing function. So you use it once a quarter or once a month, once a year to audit your inline technique. And the first part of that question, I may have missed that, but hopefully I answered enough of it.
I think there's time for 2 more questions. Do you have a preferred multivariate data analysis software?
Well, I've used a lot, and each one has its strengths and weaknesses. And I would say that, I generally have lots of software open at the same time. I have Excel open sometimes because it's really good as a spreadsheet. I have Origin open sometimes because it's really good at doing some fittings and figure making and stuff like that. And then your chemometrics multivariate software packages, like I said, do have different strengths and weaknesses in terms of how they push data into and out of your calibration and validation data sets. I do this constantly, right? Controlling the center of my model. So I'm not going to come out and, I don't want to play favorites at this point, but I've certainly used Unscrambler and Simca and Pirouette, and I think that they all have their interesting capabilities. So I invite you actually to do the same, to talk to them, to understand how you want to break that data down and present it. Generally, it's going to help you figure out which of those software packages is best for you.
Right, thank you very much. Then I would also like to encourage you to also apply as a speaker and share your experience with us. We continuously have different thematic focuses and diverse audience, so please get in touch with us. And then on behalf of Hellma, I would like to thank Chad once more for sharing such an insightful talk with us today. Also, I would like to thank the auditorium for your participation, and I'm looking forward to seeing you the next time. Goodbye.